Hello everyone, this is section 16.3, Path Independence and Conservative Vector Fields. So last time we saw line integrals, and now we defined the concept of path independence. And it's basically that no matter what the vector field is, the path along these two different curves is going to be the same. The integrals will be equal. So it's basically saying the work is independent of the path, because this is our formula for work, as you recall from last time. And the only concern is the endpoints of the path. So, for example, to illustrate the idea, if you have two endpoints, so here's your starting point and here's your ending point. If you take a curve, doesn't matter if it's what shape it is, but let's call that C1, and then you have a different curve, maybe call that C2. A lot of times these are really just straight lines, but just to or line segments, but the whole concept is that it doesn't matter what path you take. If the endpoints are the same, then the work's going to be equal. Okay, so we say it's conservative. So we further define what we mean by conservative. If this vector field is of the form, we have a function of x and y times I, and a function of x and y times j, which we're calling m and n respectively. If the partial of m with respect to y is equal to the partial of n with respect to x, then we say they're conservative. And, that's obviously a formula you write down on your cheat sheet, but it's kind of easy to remember. Just think of opposites, like I is x, so the opposite is y, and there's the partial with respect to y, and so on. So if it is conservative, if the vector field is conservative, so it satisfies this condition about the partials, then these things are true. The work's going to be 0, and it's along the closed path. That little circle there on the integral means that it's a closed path. That means it comes back to itself. So, for example, you have a starting point the same as your ending point. Okay, so that would be closed. So that's why the work is 0, because you didn't move anywhere. You just went around in a circle or whatever. So that's closed, and it's referred to as being simple as well, because it doesn't cross. If you have a function that, let's say, crosses and comes back, that's closed, but it's not simple. Or if you have a function that this is not closed, so a function that doesn't come back to its starting point, and it's not simple because of the little curl. And then, of course, if it's just a line segment or something, doesn't come back, it's not closed, but it would be simple. Okay, so then it's if it's conservative, we say that the work is 0 on a closed simple path. It's path independent, so as we stated here, and there's some function out there that we call the potential function, such that if you take minus the del operator of the potential function, so remember del is really just the derivative, it's going to equal the vector field. And furthermore, the integral is going to be equal to the potential function from the starting point, almost like the definite integral, but it's the starting point, p sub 0 minus the ending point. Evaluated, the potential function evaluated is going to be that integral. And also that the fact that this implies that f of xy is del times p, the potential function. So that's going to be, because del is equal to, recall, it's an operator, it's the partial with respect to xi plus the partial with respect to yj, and del of p is going to be the partial p with respect to x times I plus the partial p with respect to y times j. So that's what this would imply, that f of xy is going to be minus that del of the potential function. Okay, so this example asks us to show path independence and evaluate by finding the potential function. So first off, we can form the function. So I'll do it over here. The potential, or the vector field f of xy is going to be the 4x cubed plus 9x squared y squared times I, and then plus the 6x cubed y plus 6y to the fifth times j. Okay, so you just take out the respective components of their differentials. I, y is j. And so, since the function in front of I represents m, and the function in front of j represents n, to show path independence, it has to be conservative. So therefore we have to take the partials and verify that that statement is true. So the partial of m with respect to y is, okay, x is a constant, so derivative of 4x cubed is 0. X is a constant here, derivative of y squared 2y times 9x squared, 18x squared y. And the partial of n with respect to x is, now y is a constant, and the derivative of 6x cubed is 18x squared, so 18x squared y, and then if y is a constant, the derivative of 6y to the fifth is, of course, 0. So since these two partials are equal, that's what we set out to show, then we could say, well, you could say they're conservative, which leads to all of this. But conservative implies, oh, I'll just say PI, path independence. Okay, so now how do we find this function, P, the potential function? Well, it relies on the fact that the derivative of P with respect to x is the coefficient or the function in front of I in the vector field F, and also that the derivative or the partial of P with respect to y is the function in front of j. So basically you could say that dp dx is really the m, or the partial p with respect to x is really m, and the partial p with respect to y is really n. So what we could do is consider that the partial p, start with one of them, which typically will start with x. We'll say the partial p with respect to x is equal to m, which means that the partial p with respect to x is this 4x cubed plus 9x squared y squared. Okay, and then what we're going to do is we're going to try to find p. So then we're here. So now we could say that the potential function, it's a good idea at that point to introduce functional notation and say it's a function of x and y. Since this is the derivative with respect to x, to find p we can integrate this with respect to x. And so integrating 4x cubed, we get 4x to the 4th over 4, or x to the 4th. Okay, y is a constant. Integrating 9x squared, we get 9x cubed over 3, so 3x cubed, and then the y squared tags along. So plus 3x cubed y squared. But then typically we say plus a constant of integration. But since we're integrating with respect to partials, that constant of integration could be more than just a number, because we integrated with respect to x. So a constant, where we held y as a constant. So therefore the constant could be a function of y. So instead of saying plus c, that's very important to note here, instead of saying plus c, we say plus, well, typically you could use either one, f or g, it doesn't matter. I guess I want to use g because that's what we use. We do the same type of thing in differential equations. Sorry about that. We're going to use g. When it's a function of y, typically we'll use g. If it's a function of x, we'll use f. Okay, so I apologize for that. But it's just a constant, okay, in terms of what this function is. Alright, so we have imposed this first condition, that the partial of p with respect to x is m. Now we can impose the second condition, but only after we take the derivative, the partial derivative of this potential function with respect to y. So now we take the partial of p with respect to y. Okay, so that's going to be the derivative, where x is a constant. So this term goes to 0, and this term becomes derivative of y squared 2y, so 6x cubed y plus, and then in general, the derivative of g of y with respect to y is just g prime of y, its derivative. Alright, so now we can impose the second condition. So this is like, you might want to say like this is Roman numeral 1, and then Roman numeral 2 is the second condition, that the partial p with respect to y has to equal n. Okay, so that's from our observations here. So therefore, we could set what we just found, the 6x cubed y plus the g prime of y equal to n. And n here is the function in front of the differential dy, or let's go back here, n is the function in front of j. So that's equal to 6x cubed y plus 6y to the 5th. And notice how the terms containing x vanish. And that's always going to happen because of the fact that they're partials, they're conservative. So this situation's always going to occur where at this point you'll just get g prime of y to be some function of y. Could be more than one term, but in this case just one term. And then you could solve for g of y by integrating. So integrating 6y to the 5th, we get 6y to the 6th over 6. Look at how pretty that works out, y to the 6th. Now you can add a constant. And so therefore, we go back up here to what we found earlier for p of xy. And so now we could say that our potential function p of xy is x to the 4th plus 3x cubed y squared plus g prime of y was y to the 6th plus c. Okay, but then because of math books and physics books are different, some of them have this negative like we're using here, and then this order is reversed if it's positive. So, but we're going to take p of xy then to be consistent with the way we've defined it, to be minus the x to the 4th plus 3x cubed y squared plus y to the 6th, and then we'll shove the c off to the right. Okay. Alright, so just to be consistent with our definition. So now what we could do is we could evaluate the integral without having to do it formally through integrations, where we could, because we could actually, from 0 to 0, 1 to 2, we could actually determine if y is a function of x here. We're going to do that in the next example. And then you can make substitutions and evaluate this integral formally. This would be a little bit cumbersome, so that's why we're just showing this one this way. But we'll see in the next example, multi-part problem, that's illustrates the idea. But now we could say that this is equal to the integral from 0 to 0, 1 to 2 of all of this. Okay, but by our third property, it's just p of p sub 0 minus p of p sub 1. And so that would be p of 0, 0 minus p minus p of 1, 2. And then what we're doing is we're plugging these values into the p of xy. So x and y are both 0 here, so this is just 0. We can ignore the c because you have a c minus a c, so that's going to be 0. So you're just going to have a minus 0, let's say, and then minus a minus. Now we'll put a 1 in for x and a 2 in for y. So 1 to the 4th plus 3 times 1 cubed, y is 2, 2 squared, and then plus y to the sixth is 2 to the sixth. Okay, so that's 0. This makes plus, and then we'll just have 1 plus 4 times 3 is 12. 2 to the sixth is 64. 2, 4, 8, 16. Yep, 64. And so we get 77. Okay, so we'll end right there for this part, and then we'll come back and we'll do a 5-part problem that's going to be probably like a 15 or 20 point problem on the final exam. So we'll see you when you're ready.